So today we're going to be talking about protein structure and design. So the general structure of a protein looks like this. You have the N terminus, C alpha, C, oxygen, another N, C alpha, C, and so on. And this can just be any R group. So you have certain torsion angles. Let me just first point something out. So generally, bond lengths and bond angles remain practically constant, with the exception of the torsion angles. So the torsion angles, or the dihedral angles, are, for example, between the C alpha and the C, this is psi. Between the N and the C alpha, you have phi. And between the here, so this way you can represent a protein, an omega is either 180 or 80, 180 or 0 degrees. These are just in the trans or the cis formation. So just by altering these two angles, you could basically determine the structure of a protein. So this is more usefully represented in a planar peptide representation. So a planar peptide representation is when you form a plane from these atoms. So this is C alpha, C, and your double bonded oxygen, your N, your H, and this is bonded to a C alpha, which is bonded to a C, O, N, C alpha, and H. So this forms one plane, and this forms one plane, and this, between the N and the C alpha, you have phi, and then between the C alpha and the C, you have psi. So just by altering these two planes, you can actually, this is what determines the structure of a protein. So this was first performed by Linus Pauling. He basically said and performed an experiment in that he altered these kind of, the angles of these two planes. Just think of it as kind of something like this. You have like two sticks on a ball, and this forms something like that, and you can change the orientation of these in any way. So these are still like that. So this is also represented in a Ramachandran plot, which is just a plot that lists the possible values of phi and psi. And omega is generally at 180 degrees unless it's, as I mentioned before, the rare case of 0 degrees. So this is phi, for example. This can be psi, and then it goes from negative 180 to 0 to positive 180, and this goes from negative 180 to 0 to positive 180. So here, you'll notice that if you plot the angle from each amino acid, most of them, alpha helices, are generally have negative phi, negative psi, and beta pleated sheets generally have positive psi, negative phi. So in a protein structure, there'll be many regions of empty space, because in these regions, for example, you'll have what's called steric clashes, when these kind of atoms that I showed in the previous slide, the planar atoms don't fit in a conformation because they can bump into each other. So what I've just shown here is that it's the most basic kind of method of determining a protein structure just by looking at these dihedral angles.